Section 1.1 is all about the real numbers, and we're going to start our discussion with the natural numbers. Those are the most specific of the real numbers. The notation for this is a capital N with an extra line in it, and that means the natural numbers. And those are otherwise known as the counting numbers. And they include, starting with the number 1, include all the numbers that you count with, 1, 2, 3, 4, and so on. And these brackets are indicating the set of numbers that are there, and there are infinitely many of them. The next level up is the set of integers, and that's a z with a line through it. And the integers go all the way to negative infinity, and then they include negative numbers, just negative whole numbers, 0, and the positive whole numbers or natural numbers. Now, with integers, we can combine them into something called rational numbers. Rational numbers are simply numbers of the form a over b, where a and b are both integers, and specifically b cannot be equal to 0. So some examples: 1/2, 3/4. They don't have to be less than 1, maybe 6/4. They also don't have to be in fully reduced form. Integers are also rational numbers. So for example, 1 can be written as 1 over 1, or 0 as 0 over 1, and -4 as -4 over 1. Those make them all rational numbers. Now the numbers that are not rational are just called irrational. So irrational numbers have no symbol, but they are numbers such as pi and e, and they cannot be written as a ratio of two integers, and furthermore they do not have a repeating decimal. So if you look at the decimal equivalent of pi, it goes on and on forever with no pattern indicated in it. Now, some properties of real numbers. First of all is the commutative property, and all that means is that if we add two integers, a plus b, or any two real numbers, that's the same as adding them in the other direction. So for example, 1 plus 2 is the same as 2 plus 1, so something you should already be instinctively aware of. The next is the associative property. Associative. And that just means we can reassociate the addition or multiplication as needed. So if we're adding these three numbers, we could add the b plus c first and then add the a, or we could have added the a plus b first and then added c. And the same applies with multiplication. We could multiply the b times c first, or we could multiply the a times b first. Note that the direction is always the same, it's just which ones we do first, which operation we perform first. And the last property we're going to discuss is the distributive property, and that's talking about distributing multiplication over addition. So if we multiply a times the quantity b plus c, that's the same as saying a times b plus a times c. And we could also do that by multiplying on the right hand side. That's the same as bc plus, or ba plus ca. Now in regards to negative numbers, we have a few properties we need to discuss. If we multiply -1 times a number, that's the negative of that number. And if we do that twice, if we take negative of -a, we actually get a back. And when we multiply negative outside of a product, that could be associated with either the a or the b, and we get the same result. Next, if we take a negative times a negative, we get a positive. Again, these should be fairly intuitive and something you've used for a long time. And then if we distribute a negative across addition, this is -a plus -b, or we could write that as -a minus b. This is something to be really aware of because it's a common mistake to forget to distribute it, particularly to that first term. We know we need to change that plus to a minus, but we forget the first part of that term. And then the last property is distributing that negative over subtraction. So again, we can visualize it this way, or we could say that's -a plus b equivalently, that's the same as b minus a. Notice the operations that are happening there are exactly equivalent. All right, now specifically in regards to fractions, let's look at a fraction a over b. Now the top of a fraction is called the numerator, and the bottom of the fraction is called the denominator. And one little key that I use to remember that is denominator. The d is like downstairs, that's the bottom. D downstairs, denominator, that's the bottom of the fraction. Altogether, this is called a quotient, and that's where that q comes from rational numbers. Remember that rational symbol is q with a line through it. That's the q from quotient. Some operations we need to deal with are multiplication of two fractions. Now in this case, it doesn't matter what the denominators are. They don't have to be the same. If you recall, with addition, we're going to deal with that in two different cases. But for multiplication, they don't have to. We just multiply across the tops, a times c, and across the bottoms. So that means 1/2 times 3/4, for example, is 3 over 8, multiplying the tops and multiplying the bottoms separately. Division is very similar, but the first thing we need to do is really convert it into a multiplication. So dividing by a fraction is the same as multiplying by its reciprocal. Maybe it'll look better if you write it like this. And recall that the reciprocal, so multiplying by the reciprocal of c over d is flipping that fraction, d over c. And so now we just go ahead and multiply tops and multiply bottoms. So if we have the same denominator, then all we need to do is add the numerators together. Think of it this way: if I have 1/4 of a pizza, somebody gives me another fourth, how many fourths do I have? Well, I have 2/4, and we could reduce that to 1/2 if we wanted to, just as a little side note over there. Okay. What, however, happens if I don't have the same denominator? Let's say that b and d are different. Well, look at an example. 1/3 plus 2/4, let's say. And how much do I get? Well, what we need to find is a denominator that goes into both of them. So the common denominator here could be 12. That's the first number that both 3 and 4 go into. So 1/3 plus 2/4. I rewrite that as something over 12. Sorry about that. Something over 12 plus another something over 12. Well, what do I need to multiply 3 by to get 12? I have to multiply by 4. So I have to multiply by 4 top and bottom, and I get 4 over 12 here. And here I have to multiply by 3 top and bottom. So I get 2 times 3, or I get 6 out of 12. So altogether, now they have the same denominator, altogether I get 10 out of 12. And again, you can reduce that if you want, but that's not the point. So in general, if I have these two generic, the denominator could be b over d. It could be simpler than that, but that one will always work. And what do we need to do? We need to multiply a by what's missing, d, and multiply c by what's missing there, which is a b. And so that's our rule for addition with different denominators. Here we have a sufficiently complicated example. 2 over 2/3 minus 2/3 over 2. So we need to apply all the rules that we've talked about so far. So we know that dividing by a fraction is the same as multiplying by its reciprocal, 3 over 2. And then 2/3 divided by 2, well, that's the same as 2 over 1, so its reciprocal is 1/2. We can rewrite this as 2 over 1 as well, so that we can multiply. 2 times 3 is 6 over 2 minus 2 over 6. Well, those have different denominators, so we better make them the same denominator. In this case, 6 will work. So we multiply this by 3 top and bottom. So we get 18 over 6 minus 2 over 6, where we get 16 over 6. And that reduces, if we divide both of those by 2, that reduces to 8/3 if we like. So that's our final answer. Next, we're going to talk about sets. Let's look at the example where S, a set we call S, is the numbers 2, 3, 4, 5, and 6, just those 5 numbers we're talking about. Well, the individual numbers here are called elements of the set. Those are the objects inside the set. And this particular way that we're writing it is called roster notation. We could also write it in what's called set builder notation. And that's building the set. So it's the x's such that x is an integer and 2 is less than or equal to x is less than or equal to 6. So it's some sort of rule that's telling us how to build the set. So this is called set builder. The second one here is called set builder, and the first one's called roster, just listing out the roster. There are some operations we can perform when dealing with sets. Let's say we have two sets, S being the one we just talked about, 2, 3, 4, 5, 6, and a new set T, just the numbers 4, 5, and 8. So here's our example. We're going to take the union of the two sets. So we denote that with a big U in between them. So this is the union, and the union is what they have in common. I think of that like a family reunion. We list everything. So, or not what they have in common, but actually everything in both sets. So we'll write everything down, 2, 3, 4, 5, and 6, and 8. That's anything in either set. The intersection is what they have in common. We denote that with an upside down U. That's the intersection. Think of that like a road intersection. Where do they intersect? What do they have in common? Well, 2 and 3 aren't in T, so that's not in common. But 4 and 5 are in both. So therefore, the intersection of these two sets is the set containing the numbers 4 and 5. And be careful about your notation. Intersections are sets. We should have them in brackets as the list of them, just to be clear. A couple other things on notation. The empty set is denoted with the null sign, and that is empty. That means there is nothing in it, not the set containing 0, but something that's empty. And then we also want to talk about intervals. An open interval is one that does not include the endpoints. So an open interval could be going from -2 to 0, for example. And we usually denote that with parentheses on the outside. So we're not including, not -2 and not including 0, but everything in between them. We could view that on a number line. So -2 and 0. And we're going to put an open dot at -2 and an open dot at 0. And then we'll just draw a line between them to denote we mean all the real numbers between them, but not including -2 and 0. And if we wanted to make it a closed interval, we would denote that with brackets on the outside versus parentheses. And when we wrote it on the number line, we would color in our dots. So a solid dot instead of an open dot. And again, we're just going to draw a line between them. And you can do that any way you like. If you have some colored pencils or something, you can shade that in real heavy, however you like. Lastly, let's look at some examples of combining the idea of unions and intersections with the idea of intervals. If we have the interval from -2 to 0 and the interval from -1 to 1, and we want the union, that means anything in either set. So we want to go all the way from -2 to 0. Let's draw these out. So -2 to 0, those are open intervals, so we need open dots. And then this one, I'm going to kind of put it underneath, going from -1 to 1, so that they kind of overlap here. And those are open. So anything in either of these sets needs to be written down. And note that 0 is going to be there because it's in the second set. And -1 is going to be there because it's in the first set, but the two endpoints are not. So the union altogether goes from -2 all the way to 1, but does not include those two endpoints. Now what if we do the intersection instead? Again, we're doing the same two sets, but we're doing intersection instead of union. So this is where are they in common? So look right here. Where they overlap is what they have in common. Now, anything listed here has to be in both sets. So we're going to go from -1 to 0, and we cannot include those endpoints because they aren't in both sets. So there's our answer to the intersection problem. Let's try one last problem. We're going to do the intersection of two closed sets. Now, what do they have in common? Well, they go from 0 to 2, and this time we can include the endpoints. All right, and that finishes up this section.